Hello everyone. In the last lecture of the 7th module, delta modulation, we have concluded with the transmitter and receiver sections of delta modulation. Now let us see the main drawbacks of delta modulation. Here you can observe the figure here. Here u of t represents, here you can see this staircase response is the response of output of 1-bit quantizer. In the last class lecture, we discussed that the staircase waveform, this is the output of 1-bit quantizer having a step size of delta. So you will have plus delta when the when the message signal amplitude present sample is greater than the past sample. Otherwise, there is a change of minus delta when the message signal x of t magnitude is less than current sample magnitude is less than the past sample magnitude of x of t. Now here, this is a staircase response. U of t represents staircase response, and here also you can observe the message signal x of t. So this is message signal x of t, and here you can observe that this is well and good when the amplitude levels of x of t is, you can observe a gradual change in the amplitude levels of x of t. But sometimes the amplitude of x of t may not be gradual. So there may be a drastic change from low magnitude to high magnitude. So at that instance, the magnitude of x of t is very high, or you can say that the slope of x of t is very high when compared to the slope of the staircase response, because here you are considering the step size as uniform and it is constant equal to delta. So that's why whenever the slope of x of t, if it is very high when compared to the staircase response slope, then our x of t cannot approximate u of t. Then there exists a large amount of deviation between the staircase response as well as the x of t. So this distortion is called as slope overload distortion. So you can say that the deviation between the slope of x of t and slope of u of t is called as slope overload distortion. So here, in order to overcome this slope overload distortion, you can consider the slope of u of t as very high. For example, instead of delta, if I take 2 delta here, then somehow you can reduce the slope overload error. So that is, if you make the step size as adaptive, then you can somehow reduce the slope overload distortion. This is the first drawback of linear delta modulation. And second one is, this also exists due to the uniform step size, but here the slope of x of t is very less. So in this, if you observe in the second case, so this is in the first phase. In the second phase, if you observe, here the slope of x of t is gradual. So there is a gradual change in x of t in such a way that our u of t, like minute variations in x of t are there. So if there are minute variations, due to that, this u of t is gradual, oscillates around x of t. Then also there exists a deviation between our x of t and u of t. That deviation is called as granular noise, and it is also called as idle noise or hunting. And so in order to overcome this granular noise, we can reduce the step size of step size. That is, we can reduce the value of the step size delta. So these two problems we can overcome by using adaptive delta modulation. So slope overload distortion can be eliminated by considering the step size as high, and the granular noise can be eliminated by considering the step size as low. So we can eliminate these drawbacks, and then let us calculate the SNR of delta modulation. So in order to calculate the SNR, first let us assume the signal, input signal as x of t is equal to am sin 2 pi fmt. Here, and let us suppose it is sampled at regular intervals ts. And first, in order to calculate the SNR, first you have to prove the condition to overcome the slope overload error. So here we are calculating the SNR of delta modulation by overcoming the slope overload error. So here you can, in the figure already we discussed that here slope of x of t is very high when compared to the slope of u of t. So let us calculate first the slope of u of t. Slope of u of t is the change in the y-axis divided by the change in x-axis of the signal u of t. So here if you observe, the change in y-axis is delta and change in the x-axis is ts, what we discussed. So maximum slope is step size divided by sampling period, that is delta by ts. So this is the slope of u of t. Now here so we all know that the slope overload will occur when the slope of x of t is greater than very high when compared to the slope of u of t. So let us assume, so here you can see that the slope overload error will occur when the slope of x of t is very high when compared to the slope of u of t. So here I am considering the same condition. So maximum of d by dt of x of t. So this is the term that we can say that this is the slope of x of t. If the slope of x of t is very high when compared to the slope of u of t, then this slope overload distortion will occur. So let us replace x of t as am sine 2 pi fmt, which we assumed in the last slide. So maximum into what is the derivative of d by dt of am sine 2 pi fmt? It is am for the derivative of sine 2 pi fmt is 2 pi fm into cos 2 pi fmt. So this value is greater than delta by ts. Now what here internally if you see, these are the independent factors which we can get the maximum value only if we know the corresponding value. So here, but the maximum value of cosine signal is 1. So we can replace like this as am into 2 pi fm. The left hand side portion is just replaced as am 2 pi fm because maximum value of cos 2 pi fmt is 1. So am into 2 pi fm is greater than delta ts, delta by ts. So here we obtained the maximum amplitude of message signal. If it is greater than delta by 2 pi fmts, then slope overload distortion will occur. So in order to overcome the slope overload distortion, what you have to do? You have, so this slope overload distortion will occur when am is greater than delta by 2 pi fmts. So in order to overcome this, what you are doing? You can consider am value as less than or equal to delta by 2 pi fmts. So this is a condition to overcome the slope overload error. What is that? You have to consider the am value as less than or equal to 2 pi fmts. So let us consider this amplitude for calculating the SNR of delta modulation system. Here, first condition that we have taken, that is slope overload distortion doesn't occur when the amplitude is less than or equal to delta by 2 pi fmts. We are considering the threshold value as am is equal to delta by 2 pi fmts. Now we already considered x of t as am sine 2 pi fmt. For this signal, the signal power P is defined as V square RMS by R. Here the maximum amplitude is AM. So I can replace V RMS as AM by root 2 because the maximum value is AM. The maximum value by root 2 is our RMS value. So AM by root 2 whole square divided by R. So you can get it as AM square by 2R. Under normalization, if you assume R as 1 ohm, you can get it as AM square by 2. So to overcome the slope overload distortion, you can replace the maximum amplitude from equation 1 in am square by 2. Let us substitute am in the signal power expression. Then you can get signal power as am, that is delta by 2 pi fmts. So delta by 2 pi fmts whole square divided by 2. So 2 square into 4, that's 4 into 2. So you will get it as 8 in the denominator. Delta square by 8 pi square fm square ts square. So with this you can calculate the signal power as delta square by 8 pi square fm square ts square. Now let us substitute this signal power in the SNR expression directly to get the SNR of DM system. So before that, let us calculate the noise power. Here we all know that the distribution of quantization error is uniform from minus delta to plus delta, because when current sample amplitude of x of t, if it is greater than past sample x cap of t, then amplitude will rise by a factor of plus delta. Otherwise, if x of t is less than the past sample, then you will have a step size variation of minus delta. So that's why our distribution is from minus delta to plus delta. If the distribution is uniform, we know that it is uniform. So the maximum amplitude will be 1 by maximum upper limit, that is delta, and minus of minus lower limit, that is 1 by delta minus of minus delta. So you will get 1 by delta as the maximum amplitude of the probability distribution function of error function in DM system. So Fe of E is equal to 1 by 2 delta when the error range from minus delta to plus delta, otherwise it is 0. When the error is less than or equal to minus delta, we know that the distribution is 0. And similarly, if error is greater than delta, here also error is 0. Okay, here we calculated the probability distribution function. And we know that already we calculated by using the same expression in PCM. So noise power is defined as V square RMS of noise signal by R. Here, the mean square value of the error signal can be defined as expectation of E square, which is equal to integral minus infinite to plus infinite, E square into Fe of E dE. But we know that the error signal distributes from minus delta to plus delta with an amplitude of 1 by 2 delta. So let us replace Fe of E as 1 by 2 delta in the range minus delta to plus delta. Then you can get the noise power. So expectation of error square is equal to integral minus delta to plus delta E square into 1 by 2 delta dE. So let us take this 1 by 2 delta outside the integration. 1 by 2 delta into E square integral E square dE. So it is E cube by 3. That range from minus delta to plus delta. Let us substitute the upper limit and lower limit. So delta cube by 3 minus of delta by minus delta by 3 whole cube. So minus of minus, it leads to plus. So you will get 2 delta cube by 3 into 1 by 2 delta. 2 gets cancelled to lead the quantization noise power of DM system as delta square by 3. So noise power will be delta square by 3 divided by R. Normalized noise power can be obtained by taking the R value as 1. So finally we obtained the normalized noise power of DM system as delta square by 3. Here you can see that, for example, if you assume the normalized noise power, if it is distributed from minus Fs to plus Fs, and also let us assume the low pass filter cutoff frequency at DM receiver be W. At the receiver, we will use the low pass filter, which has a cutoff from minus W to plus W. Let us assume. Then the output noise power will be W, that is the cutoff frequency of low pass filter, divided by the maximum sampling frequency multiplied by the actual noise power, that is delta cube by 3. So finally we will get the output noise power considering the low pass filter cutoff as W is W by Fs. I have taken 1 by Fs as Ts. So W into Ts into delta square by 3. This is the normalized noise power considering the low pass filter cutoff frequency at the DM receiver as W. Now please substitute the normalized signal power and normalized noise power in the SNR expression. So signal to noise ratio is equal to normalized signal power. So we obtained it as delta square by 8 pi square fm square ts square. And similarly, we obtained normalized noise power considering the low pass filter cutoff as W is W into Ts into delta square by 3. Here delta square gets cancelled and we will get SNR of DM system as 3 by 8 pi square W into Fm square into Ts cube. This is the expression for SNR signal to noise ratio in delta modulation system. For example, if I assume the low pass filter cutoff frequency at DM receiver W is equal to some FM, where FM is the maximum frequency of message signal. That is, if I assume the low pass filter cutoff as minus FM to range as minus FM to plus FM, that is same as maximum frequency of message signal, then signal to noise ratio can be written as 3 by 8 pi square into W you can replace as FM. So Fm into Fm square into Ts cube. So here you have Fm into Fm square. I can write it as 3 by 8 pi square Fm cube into Ts cube. So this is the SNR of DM system, assuming the low pass filter cutoff equal to the maximum message signal frequency range. That is equal to 3 pi. If I take 1 by Ts as Fs, I can write it as 3 pi Fs cube by omega m cube. Here you can conclude that the SNR of DM system is inversely proportional to the cube of maximum frequency of the message signal. That is, if you increase the value of maximum message signal frequency, it will reduce the SNR of delta modulation system. In this module, we have concluded that transmitter, receiver, sections of delta modulation, as well as we calculated the SNR of DM system. With this, we can close the module of DM system and we can continue with the adaptive delta modulation in the next class. That's what you can see that in the next module, we can continue with the adaptive delta modulation. Thank you for listening.